Okay, so that's good. Okay, so now you can see, you can hear me, you can see me, right? So you, all of you already knew that I just postponed the test, and I already give the reason that why I did that, right? And I got a few emails, like as I said before, from your friends, especially who live in the dome, and from others also, like they're having kind of difficult time to manage, like to in this transition, right? No. The material that you are covering this week will not be in the test. The test again would be from 6 to 9. The test is still going to be from 6 to 9, right? So that the material that we covered this week will not be on this test, exam 2. Okay, good. So we only do the, I mean, the material that we covered today will be on the next test. Okay, so far so good. So we can now start the new chapter, right? And again, this chapter will not be, I'm still having trouble to identifying what angle is being given in magnetic flux problems. Okay, so magnetic flux problems, usually what we have here is that how we define magnetic flux is that this is magnetic flux phi B, right? So in this case, we can write B A cosine phi, right? And this phi is the angle between, this phi is the angle between B and the perpendicular to the plane of the coil. So that means perpendicular to the plane of the coil means it depends on like how the coil is oriented. We define this way. For example, if we have a coil like this, right? Then this is magnetic field, and this is the orientation of the coil, but perpendicular of the coil would be like this, right? You understand? So this is the perpendicular to the coil, this line. So we can write this as a N, like the normal, right? So this is N here, perpendicular to the coil. So this angle is phi. Sometimes, if problem says that field makes an angle something with the coil itself, right? For example, this is the coil axis here. This angle, sometimes this angle is given. For example, if magnetic field makes an angle 60 degree with the coil, this angle is 60 degree, right? In some cases, you can see that if the magnetic field makes an angle 60 degree with the coil, this angle is 60 degree, right? So that means this is not the phi angle, but this angle is phi. So phi would be how much? Phi would be, yes, 30 degree. That is 90 degree minus 60 degree. So that's the important point. So you need to understand is that. So how we do, right? So this is how we do. Good. So far so good. Now you understand now? How would you do? So if the problem says that magnetic field, if magnetic field makes an angle something 30 degree with the perpendicular to the coil, so that is what we will need, right? But if it says that magnetic field makes some angle with the coil, then that is not the angle we are looking for. right? If the given angle is directly the angle with the coil, then we need to find the angle that that is with the normal, and that will be the 90 degree minus this given angle. So if the angle is not perpendicular to the coil, it is not the angle we are looking. Yes, yes. The angle has to be the angle made by magnetic field with the perpendicular to the coil, right? If the angle is given as the B makes an angle, for example, 60 degree with the coil. With the coil means coil itself, right? I can show you here. So look here. This is the coil, right? This is the coil here. You can see. So this is the perpendicular to the coil, right? Now, if this is the perpendicular to the coil, this is the coil, this is perpendicular to the coil, and this is the magnetic field. So this angle here that I'm showing right now, this angle below this thing here, this angle is not the angle we are looking for. This angle we are looking for, right? So this angle is the angle that B makes with the coil, like this that I'm showing here, right? So we always look for the angle that magnetic field makes with the normal. Good. Now, I mean, okay, tell me what is your confusion? I mean, Snell's law is the law that when light moves from one medium to other. So if there is no refraction, then you do not use Snell's law, right? I mean, if the light moves from one medium to other, if the light changes the media, right, that means it enters from one medium to other, right? So that means you have one medium like this. You have one medium, you have other medium. This I said that medium one, medium two. Then if the light enters from one medium to other like this, depending on how the medium's refractive index, then you can use Snell's law here if you want, right? But if the light it does not move from one medium to other, or the refraction is not there, if there is a case of reflection, then we don't use Snell's law. For example, if this is the reflecting surface here, right? This light goes in like this and this. Then in this case, the light is not entering from one medium to other, right? So that means we do not have any refraction there. We cannot use Snell's law here. So we can use Snell's law here. Wherever light goes from one medium to other, in that case, we use Snell's law. Does it make sense now? Good. Good. Okay, so let's move to the next chapter now. This is chapter 24. Okay. This is chapter 24, and this is about the physical optics. Good. So physical optics means in this chapter. Oh, sorry. Thank you for reminding me. Okay, now recording is started, okay? Good. Thank you. Now, so physical optics means in this chapter, what we do is that we just learn about the how the images are formed. Basically, we learn about the objects and images, right? So right now, if you stand in front of the mirror, plain mirror, you can see your image, right? And you can see the image of the cars that behind you, right? When you look your rear view mirror. So all these kind of things, or if you have the right now, I'm putting on my glass here. So that means I can see the object through the glass, right? So that means that there are two ways that I can see the images. One is by reflection and the other is refraction, right? So all these things that we learn here, and that is called the physical optics. So to know that, I mean, to know about the how images will form, you need to know that at least we need to have two rays, right, that will be reflected or refracted through any surface, and they can meet, and where they meet we can see the image. Okay, so we start with this first one in here. First one is 24.1. Again, it doesn't matter. That would be the reflection at plane surface. Okay, so what does this mean is that we already did that, but we in this topics, what we try to do is that we just try to learn how the in the plane surface how the images will form. For example, the plane mirror, right? Look here. So we have this kind of things. We have the plane mirror like this. So this is the polished surface. Then let's start with the point object. Object can be of any shape, right? This object, I can take this object, this marked as object. So this is not the point object, it has some height, right? So if we start with some point object, then what happens here is that this is the point object here. This is my object. Object is called O for the object, right? Now, so, or I mean, in this chapter, we usually stick with the oh, it's fine for object, that's fine. So now what happens here is that a light ray goes from this point object like this and strike on the mirror. Then what happens? It will reflect it back, right? It will be reflected back. So this is the normal here. So it will be reflected back. You understand? Everyone? Right? Good. Now, so we can do another one also. If the light, generally we did not do that before. If the light from one object, number of light ray can come and strike on the mirror, right? So for example, now if this light, if one light goes directly downward like this, making 90-degree angle, can you tell me how this light will be reflected? Anyone? If the light goes directly through the normal like this, right? If you draw the normal here, right, that means this is the incident ray. If you draw the normal here, we don't have any incident angle, right? Yeah, straight back, that's right. So that means, look here, this is the ray. If you draw the normal here, we don't have any incident angle. Incident angle is 0. Incident angle 0 means reflected angle also has to be 0. So that means it has to go back. Now it will reflect back. So that means this ray has both incident ray going down and then reflected ray going up. So to see the image of this object, look here very carefully. To form the image, or for us to see the image, this is a reflected ray. This is another reflected ray. I can say this is the reflected ray 1. This is reflected ray 2, right? So these two rays should meet, has to meet somewhere. If these two reflected ray can meet, right, then there we can see the image. So now look, this reflected ray is going this direction, this ray is going that direction. Can they meet at any point here in this side? No, right? So that means these are the real rays. These are the real reflected rays. So that means these real reflected rays cannot meet this side because they are diverging. This go like this go like this, right? They cannot meet. You can draw another one, you see? You can draw another one here. And if you draw, then that will go like this. Again, they will not meet. I can show you another one, but you don't have to draw it. Just for your idea, if I draw another one like this, another ray, then you have to draw a normal here, then that will go like this. You see? Now, can these two rays meet? No, these three rays cannot meet because they are like divergent, right? So that happens. So we don't need three rays to understand. I can have only two rays. So as I said before, one thing is that you have to understand, one point I write here. Image is formed where two reflected rays meet or appear to meet. Look, this is one conclusion here. So image will form where two reflected rays meet or appear to meet. So that means, what does this mean, appear to meet? In this situation, at least two, we can have three or four. Just add this word also, at least two, right? So that means then look here, these two reflected rays cannot meet. So that means this is the dawn, two reflected rays meet, so they cannot meet. But let's find where they appear to meet. So since they cannot meet same side, what we do is that now we just produce these rays like this. We just produce these rays like this, and they appear to meet here. You understand now, everyone? In the situation where these two reflected, at least two reflected rays cannot meet in real, right? Cannot meet in real, then in that case, what we have to do is that we have to produce these rays. Produce means this, right? So that they can meet. These rays is going up, this is going this direction. They cannot meet this side, but if we produce these rays, opposite side, they can meet, right? You understand now? We have to figure out the point where they can meet, either in the same side. That means they, in that case, we say that these real rays meet. If these real rays cannot meet, then we have to produce these rays on opposite side, right? Where we can find that these two rays appear to meet. Now, this ray, and because they cannot meet this side, if we produce this ray this way and this ray that way, then they appear to meet here at this point. You still understand, right? First situation is that we need to look whether these two reflected rays can meet this side, right? This side means the reflected side. If they cannot meet on the reflected side, then what we need to find is that we need to produce these reflected rays, right, behind the mirror, right, to find as if there is one point that they appear to meet. It's not the real, but it's just to try to find that where they appear to meet. Good. So that means at this point now, these rays appear to meet here, so the image will appear to form here. The image will appear to form here. So that means since this image of this object, now you have idea that when you look in, when you sit in front of the plane mirror, you feel that your image is behind the mirror, right? You understand now, everyone? When you see your face in front of the plane mirror, right? You feel that your image is forming behind the plane mirror. At least you understand that part, right? So that's what's happening. Behind the plane mirror means, look, this is you, right? You are staying in front of the plane mirror. So when you look on the plane mirror, what happens is that the light rays that going from your body that strikes on the mirror and they reflect back, they cannot meet in front of the mirror, right? You can easily see this here. So that means those rays now appear to meet behind the mirror like this. So that means those rays appear to meet behind the mirror means somewhere, at some point where those rays appear to meet, you see your image there behind the mirror. So that means since these rays are not real, okay, you can put a mirror here and you just sit, I mean, in front of the mirror, and then you just feel that your image is forming behind the mirror, right? Then if you ask your brother or sister to go behind the mirror and to look whether there are any images forming there, or if you put some I mean screen there, you cannot see any image there because those images are not real. These rays are not real. These lines are not real, right? These are just the produced line. So that means when the real rays like this do not meet, and if we have to find the image point like this, then these images are not real images. They are called the virtual image, and we cannot locate those images in the screen because they are not real. They just appear to from there, and there's nothing behind the mirror. You understand now, right? So that means the whole point is that at least to form the image, at least we need to have two rays, right? They either meet, the image either may form on the same side as the reflected rays here, but in this case that's not the true situation, or either they appear to meet here, then in this case this image is virtual, right? What does that say? Image is formed where at least two reflected rays meet or appear to meet. Two reflected rays. You need to have two rays, right, where they meet or appear to meet. Two reflected rays, yeah, meet or appear to meet. So now, at least we know that here. So, I mean, if the image is formed on the same side of the reflecting surface as the, you understand me, right? As the reflected rays, then image is real. But now reflected rays this side, the image is forming other side. So now this image is not real. Okay. So I write it here for you. After this, sign rule for object distance and image distance. Sign rule for object distance and image distance. So now let's define two things. Object distance is the distance from the mirror. Look here, from this, right? And then this distance from the mirror to the object. This is object distance. This is written as S. And this is image distance. This is S prime. Okay. So I write this here for you. S is object distance. That is the distance of object from the mirror. From the mirror. S prime is image distance. That is distance of image from the mirror. Mirror reflecting surface. Right? Do you have any problem with this? No, right? We can see that here. This is mirror, this is reflecting surface. distance of object from the mirror. For example, your mirror is here, right? And you see you stand here, so distance from your mirror to you, object distance, right? And then where your image is formed or appears to form, and that distance from the mirror is the image distance. Okay, what is your confusion, Hannah? I Okay, object distance is from the mirror. Okay, you have any mirror here. So the mirror and you are here. Distance from mirror to object is object distance. Distance from mirror to object is object. This is object distance S, right? And where the image is appear to form or forms, the distance from mirror to the image is image distance. Oh, sorry. I thought that you have confusion. Okay, it's my bad. Okay, now good. So now look here, everyone. Now I write the rule here for you for this object distance and image distance, and then you can just after that we can easily define what kind of images are real and what kind of images are virtual. Okay. So can I erase this part here? Good. Now I erase this part here. Now I write the sign rule for object distance and image distance. Okay. Look, this is the sign rule. First one is for here. This is the sign rule. S and S prime. So first is for S. S is usually, I mean, positive, but still I need to, you understand. If the object is same side of the reflecting if the object is same side of the reflecting surface as the incoming rays, that means incident rays, object distance is positive. So S is positive. Otherwise, negative, right? So, okay. What does this mean is that if the object is same side of the reflecting surface as the incoming rays, incident rays, S is positive, otherwise negative. So if you understand what it says, and if you look at this figure right now, this S is positive or negative. If you understand this statement, positive, yes, good. Frank said it's positive. It says that if the object, this is the object, right, is same side of, this is the reflecting surface. If the object is same side of the reflecting surface is the incoming rays, this is the incoming rays, right? So incoming rays are this side and object also same side. So that means in this situation, object is positive. So usually we will have this situation. We don't have to worry about object distance because object is always real thing. So that means when the light comes from the object, this light and the object, they will be on the same side. You understand my point, right? So that means usually this S will be positive, right? For any virtual object that may be negative, but we are not doing this right now. So right now this object is here and this object is on the same side as these incoming rays of the reflecting surface. So S is positive. Same way we can define S prime, right? Okay, for S prime, same way. So let's define this. If the image is same side, I can write on the same side. Same side of the reflecting surface. Same side of the reflecting surface as the outgoing or reflected or reflected rays. S prime is positive, otherwise negative. If the image is on the same side of the reflecting surface as the outgoing or reflected rays, right? The S prime is positive, otherwise negative. Okay. So now if you understand the definition, this definition, then can you tell me this S prime here, this S prime is positive or negative? Negative. Good, good. Negative. Yes, everybody is good so far. So if, can you explain? Okay. What it says here, if the image, right, is on the same side of the reflecting surface, if the image is on the same side of the reflecting surface as the outgoing or reflected rays. So these are the in this case, these are the reflected rays, right? This is reflected ray, this is reflected ray. So these are the reflected ray, this is the reflecting surface. So outgoing rays are this side, outgoing rays are on this side, reflected rays are this side. However, image is opposite side. If you see very carefully, if the image on the same side of the reflecting surface as the outgoing rays, this is the outgoing rays. So if the image is formed on this side, then it will be positive. Otherwise, it will be negative. You understand now? So these are the this is outgoing rays, this is the outgoing ray, these outgoing rays, this is the reflecting surface. So these rays are on this side of the reflecting surface. However, image is being formed here, other side. So that means this image has to be negative. You understand now? Good. So now it's clear now here, in this particular situation here, for in this case, of plane mirror, we can say that S is positive and S prime is negative. So that's why now we can see other way around also. No, image would not be always negative. It depends on how it is formed. In case of plane mirror, it is always negative if the object is positive. But if you have the curved mirror like this, like the concave or curved like this, right, the saving type of mirror or something like that, or I don't know, these days people use those kind of mirror, but when we grow up learning science in our high school, we used to uh, hear that at that time that the makeup mirror would be like this, right? And then you can have that kind of thing. So those kind of mirror can give you the same side image, right? In that case, we have the positive image also. I can show you later, right? But right now, this kind of plane mirror can give you, always gives you negative S prime, and the image is virtual. One more conclusion is that if this image distance is negative, the image is virtual. If image distance is negative, image is virtual. If image distance is positive, image is real. Right? Now it makes sense. For the image distance to be positive, the image has to be formed on the same side, right, as the outgoing rays. If this is the case, then we have the positive image distance. Good. So now, if S prime is for positive S, for positive S prime, image is real. We have not seen this so far. For negative S prime, image is virtual. So virtual image means S prime would be negative. Good. Now, one thing that we define here about the sign convention, and the other thing that in case, at least in terms of the plane mirror, if we use the geometry, you can easily see that this S equals to S prime. Can I erase this part again, top part? Can I erase that? Good. Okay, now I'm erasing this here. Good. Okay, so in this case, for plane mirror, this line and this line has to be equal. S equals to S prime. Okay, I'll give you 1 minute, all of you, to figure out geometrically, right, how these two line segment are equal. If you could not figure this out in 1 minute, then you can ask me. Can you help me? Okay. Your time starts now, and I'll take a sip of my coffee. Kind of, Kevin. Yeah. What angle? They have the same angle line, not very clear, but you mean to say this angle, maybe opposite angle, right? In any triangle, if the opposite angle are same, if this angle and this angle are equal, then these two sides are equal. That means this. If this angle and this, if these two angles are equal, then these two sides have to be equal. You have to look at that. Good. Yes. Now it's easy. Now it can be easily seen. We know that this angle is I and this angle is R, theta I, by the way, and theta R. So we know that theta I equals to theta R. This is from law of reflection. These two angles are equal, right? So that means if these two angles are equal, then these two angles, look here, this angle is, look this side here, right? And whatever we have, this is 90 degree minus this is 90 degree minus this, and these two total here, this is 90 degree, right? And that has to be the 90 degree minus this. Or if you see this here, right, then you can see these two angles are equal, and then same way for these two angles. So these are same angles, so that means these two sides are equal. Because this angle here, right, this angle and this angle has to be equal, and this, if you draw this line, this angle and this angle has to be equal, right, here. And then if you do that line here, this angle has to be equal. There are a number of ways you can do that, but these two angles are equal. So that means these sides are equal. So this is always true, that this S equals to S prime, at least for plane mirror. So this is how we know. Important point here is that this plane mirror is not very important thing. I mean, we will do a few of those, but important is that here in context of plane mirror, we define the sign rule, and we know that how images can be formed, right? And we know that the plane mirror can only, can you zoom in the camera in the board? You cannot see. I cannot zoom in the camera in the board. I mean, if I do that, let me see. I have to move it a little bit further. But yeah, I mean, you cannot see this. You should be able to see this, right? Mm, Is it okay now? Okay, because I just moved a little bit further. Good, good. Yeah, now, good, good. So now, this is here. So important thing is that this, when to form the image or to have the image, at least we need to have the two rays, right? And if the two reflected rays meet, right, then we have the reflected ray mean the same side of the reflected rays, then we have the real image. Otherwise, we have the virtual image. Okay, that's good. So now, can we move to the next part? Good. And the next one is that, like I mean, about your question, what we need to do is that we need to learn about the reflection in the curved surface, and we are doing this now. Very good. Okay, so now let's do this. Maybe this is 24.3 or 2. It's okay. This is the reflection. This is the reflection at curved surface. This is the reflection so now there are two types of curved surfaces. First, I would like to explain that. One is this. The reflecting surface is curved inside. So this is the polished surface. This is the reflecting surface, right? And the other one is like this.
Professor,
Mm-hmm.
you're not recording anymore.
Oh, sorry. Thank you. Now, okay, I repeat it again. Okay, now this is another one. So that is reflection at curved surface. Good. Now there are two types of surfaces. One is this. That means the polished surface is up, right? I still remember that my high school teacher used to say me like this. So like this is curved upward. I don't have that big, but anyway. So this is not the one. But if I show this, if you see here the cup one here, right? So this is the polished surface, right? The curved surface here, this is the reflecting surface, right? This type of this one. And the other one like this, polished surface is inside. You understand now, right? They are different. Now this is the reflecting surface, right? So this is the reflecting surface like bulging outward, like this. Light comes in here, and then it just reflected from this surface, right? This is this. And the other one is that this one here, light comes in, the cup, right? And then it comes outward. Okay, good. So this type of surface is called, this is called the concave by the word. You understand, right? This is concave. You're okay with that, right? It makes sense. Concave. Good. And what about this? Do you have word for this? Have you ever seen this kind of before? If this is concave, yes, convex. Yes, good, good. So this is convex. So now, depending on their shape or depending on their geometric shape, right? This is concave, this is convex. So we first do with this convex, I mean concave, we define everything. It is easier to understand with this. And then later we do with the convex some example. So look, so this is the only a part of the concave or convex surface. What does this mean is that, so Christmas has just been passed. So if you still remember, so you have the ornaments that you are trying to put on the Christmas tree. So those ornaments are like spherical, right? You understand? Those spherical balls, right? So that means, you imagine now you have that spherical ball ornament, right? And then that's the whole spherical ball is a mirror. You understand my whole point? Is the reflecting surface. So now the whole spherical ball is a mirror, and that is the convex, because that's the bulging outward. You understand my whole point? So that means this is a part of that whole spherical mirror. If you cut a slice, you understand now? If you cut a slice there from one side, and you will get this part. You're following me, right? You understand? Like, I mean, if you cut the watermelon slice, that means this is this, and this is the reflecting surface. The same thing happens here. If you have the like the concave surface, right, but that is the polished outside, then that a part of that would be this. So now, so you have if you have this spherical surface, that means that surface will have a center in the middle, right, everyone? You have a spherical surface. This is the only a part of that spherical surface. So that means that sphere has a center in the middle. You understand, right? So that means now this is this center here. If I draw this center here, and if I draw a line passing through that center, now this makes sense. So if you complete this through this, then this makes one sphere, right, everyone? And this is the center of that sphere. And this is the one cut part. Good. Now, this is called the C, right? So this C is called the center of the curvature. Center of the curvature means center of the sphere, right? Whole curvature. Now, the distance from this means the where, like you have this whole thing. Then when this line, by the way, what is this line here? What is the distance between from here to there? If this is the center of the sphere, what is the distance between this point to that point? Yes, yes. This is radius, obviously, in geometric sense. And we said this point is V, right? And this is the radius of curvature. So that means from this point to that point, this is called R, and R is called the radius of curvature. R is called radius of curvature. And where the exactly on the mirror, right? So this is spherical surface. I have cut one piece. So it goes like this and meets on the mirror, right, on the surface. And this point is called the here, right, vertex or pole, right? So V is called vertex. VERTX, vertex or pole of the mirror. These are just the names, right? Now, in this case, what we are trying to do here is that we are trying to get one equation. That is the very, very famous equation to do this kind of reflecting surface. This is called the relation between object distance and image distance, right, everyone? Okay. So let's do this. Let's have a point object somewhere here. I have a point object O, right? And then this is the mirror here. So a light ray goes like this, a little bit up so that I have space, enough space. Strikes here. And then this will reflect it back, making these two angles same. This is normal here at this point. So that means this angle and this angle has to be same, right? And this normal obviously will go through the radius because radius always makes normal, right? Now, one ray will be going this line, one ray will be going this line and reflected back. So now, this is the one reflected ray, this is other reflected ray, these two reflected ray meet here and image is forming here. Okay, I can show you here. This is our object here. Then one ray is going like this, reflected back and come here. Other ray is going straight. It has to reflect back, same path. This reflected ray and this reflected ray, these two meet here, right? So this is our image point. So that means now this is S prime. From here to there is, if I write this here, from here to there is S primed. And then from here to there is S. Right? You guys done with the drawing? You guys done with the drawing or you need more time? Done. Okay. So, yes, I was about to ask this. You are way ahead. Okay, that's good. Now, so now let's look at here. This is our S. This is our S prime, right? So if you go back and look at the rule that we defined, sign rule, then can you tell me what about this S and S prime? They all are positive. One is negative, other is positive. What happens here about S and S prime? Let's start with S. S is positive or negative? S is positive or negative, everyone? Now you, good. What about S prime? Now, the S prime is on the same side. This is the reflecting surface, right? The image is on the same side as the reflected rays. Now you understand, right? So this is the reflected ray, this is the reflected ray. So these two are reflected rays, and these are this side of this reflecting surface, and image also on the same side of the reflecting surface, right? So that means this is also positive. So that's how I explained you last time. So when we do the curved mirror, then we see that happens, right? So now this image is on the same side of the reflecting surface. So both are positive here. So far so good. So we understand that. So we will do it again later for this convex part, since I need this space to do some math. So I'm just erasing it, okay? Now here, what we are going to do is that we are going to find, sorry, isn't the reflection surface is the outside? No, inside. This is the reflecting surface. Outside is the polished surface. This is the polished surface. For convex, reflecting surface is outside. For convex, reflecting surface is outside. Good? Okay, now. Our target is to find relationship between S, S prime, and this. So our target is to find relationship between S, S prime, and R using geometry. So now here comes the geometry thing. So we need to find S, S prime, and R. Okay. So look, if I say this angle is alpha, this angle is phi, and this angle is beta. Right, everyone? Good. Everyone okay with that? Good, good. Now, if I say this angle is theta, this angle also has to be theta because they are equal. Good. What is the word after it? Relationship between? Yes, between. Now, this angle is theta, this angle is theta. Okay, if I have this, then if you look here in this triangle, everyone, in this triangle here, this is alpha, this is theta, this is phi or phi. I can write phi equals to alpha plus theta. And in this triangle here, I can write beta equals to phi plus theta. Look at the triangles. If you do not understand, then I can explain it. Okay? You are okay if I write this? Look here, only in this triangle here, everyone. This is the external angle. This external angle will be equals to sum of, right, in adjacent interior angles. This is exterior angle. This external angle will be equal to sum of in. This is the adjacent angle. These are the in adjacent angle. So this is from geometry. This should be this plus this. Similarly, in this triangle, this beta equals to this plus that. This is from geometry. Good. You understand? So now this is this. So if we eliminate theta, because we do not need theta, so what we can do is that now theta equals to, what we do here is, okay, this one would be here. If we subtract these two, phi minus beta equals to alpha plus theta negative phi plus theta. Can I do this? I just subtract left hand side and right hand side. Phi minus beta, alpha plus theta minus phi plus theta. This is phi, this is alpha, and this is beta. Good? You understand now? Good, good. Look here. This is from geometry. This phi equals to alpha plus theta. This beta equals to phi plus theta. Now what I'm doing is that I'm subtracting these two left hand side and subtracting these two right hand side. We can do that. If we do same operation, both side of the equation, we can always do that. You understand, right? So that means I have this phi minus beta, then alpha plus theta minus phi minus theta. Theta, theta cancel out. If I take this phi this side, phi plus phi, if I take beta other side, that would be alpha plus beta. That gives me 2 phi equals to alpha plus beta. I could skip this, but I would like you to know some kind of geometry here that refreshes your mind, because we are doing like different things so far. Okay. You got it now, right, everyone? Good. So we can stop here. Stop means we can just make it like this and say this is equation 1, right? So now what we do here is that if we take that these angles are very, very small angles, then this part can be taken as a straight line, this part, right? If I take all these angles, beta, phi, and alpha, they are very, very small here. If they are very, very small, then that will be very, very small here, right? Then we can take it as a straight line, right? So that means this is straight line. So we can take this, everyone. So we can take this is a right angle triangle, this is a right angle triangle, and this is a right angle triangle, right? I mean, this line here, this is a curved line for very, very big angles. But if you take these are very, very small angles, in terms of small angle range, if I take this very, very small, so this kind of straight line, right? You understand here? So that means I can take this part is a straight line. So that means if these alpha, phi, and beta are very, very small angle, so this can be treated as a straight line. Then we can treat them as right angle triangles. Okay? Now, can I erase it? Okay. So that means I write it here. Okay, for small alpha, phi, and beta, right? So if they are very, very small angles, then what we can do is that if I drop it here line so that they are pretty close. If I say this is h here, so they are pretty close. So that means this distance and this distance, they are very, very close for small angles. So I can ignore this part. So I can take this distance as this distance, right? You understand my whole point? Now these are the right angle triangles. This is one right angle triangle. This is the other right angle triangle here. But since angle is very small, I can say that these 2 points here coincide. So that means I can take this side as S prime. I can take this side as R, and I can take this side as S. You understand now? Right? Okay. So if they are very, very small angles, then what happens is that this tangent beta equals to S divided by S prime. This tangent phi equals to S divided by R, right? And then this tangent alpha equals to S divided by S. Right? We can do that. Good, good. You understand now? So for very small angles, if we write that, so tangent beta equals to S divided by S prime. And for very small angle, tangent beta is nearly equals to beta, and that means beta equals to S divided by S prime. If you do that in your calculator, for example, if you do that tangent 1.8, right, or tangent 0.8, that will come about 0.8. So if the angle are very, very small, we can replace that way, right? Similarly, tangent phi equals to h divided by r. This is phi here. For tangent phi, that will be h divided by r. This is r from here to there, right? And for a very small angle, we can write phi equals to h divided by r. Now, we do the same thing here. For this alpha, if we do that, tangent alpha equals to h divided by s, and then that would be similar h. We can write this, right? That can be written as alpha equals to h divided by r. Finish this. You got it? What does it say between the two betas? Where are between two betas? Oh, here, this. Oh, if you have very small angle, for any small angle, tangent of that angle is equal to angle itself. What I'm saying is that if you do in your calculator, for example, tangent 0.3, right? That would be nearly equal to 0.3. You can try it. You understand my point? Where did the r come from tan alpha? Where is r? Oh, not alpha. That's my bad. This is S. Good. You understand now? Everyone. Okay, that's fine then. So we have this. So if we go back equation 1, if I write it here, if I write equation 1, we have 2 phi equals to alpha plus beta, right? So what is phi here? This is phi, right? Okay, 2 h over r equals to, what is alpha here? H over s, right? Plus, what is beta here? H over s prime. Where did the r come from tan alpha? Oh, okay. You already this. Is that a 2 or alpha? This is 2 phi. I got it from equation 1. This is 2 phi equals to alpha plus beta. You understand now? Is it your question, by the way, Kevin? Is that a 2 or alpha? Your question is here? Here? Okay, yeah. This is 2. This from equation 1. Can you go up and check your note that we labeled that equation 1 there? And I got that. Okay. 2 phi equals to alpha plus beta. Then we have this. And we substituted the respective values here. Then we got this. That is 2 over r. I can cancel h because this is all same everywhere. If I cancel h, then that would be 2 over r, 1 over s plus 1 over s prime. So this is what we got so far. So relationship between this r, s, and s prime. 2 over r and s prime. Okay. Now, one thing, since we already done this part, so this is a relationship between that we are looking for r, s, and s prime. R is radius of curvature, s is the object distance, s prime is image distance. Now let's do one thing here, everyone. Now can I erase this? You already have this in your note, right, in the recording also. So I want to tell you one thing, one special case here. Okay, if the object is very far, if the object is very far, very far means like if the light is coming from like a very far hill or very far building, right, very far, then the light rays would be coming as a parallel, right, like this. You know that, right? We discussed that when we discussed the wave front, right? If the source is very far, then the rays will come as a parallel rays, right, everyone? So let's see here. This is our concave mirror. This is the radius of curvature here. But if the light ray is object is very far, coming from very far, so that means light will come like this, parallel to the surface, like this, right? So if you have try to understand what I'm saying, you can see me, right? Okay. If the light is very far, from very far, then those light ray will come parallelly like this, parallel to this line. By the way, I have not defined this. This line here, that line that we draw, this line is called principal axis. This line is called principal axis, okay? So that means for very far object, right, this line is the principal axis. So the incoming rays, they will come parallelly. And when these parallel rays, the rays parallel to the principal axis, will reflect, they will meet at a certain point, like this point, and where the image is formed. So right now, this is the image point here, right? So this is the image distance from here to there. So very far means sometimes we say that is a to infinity, right? So very far object means that is from infinity. So if when the object is very far, that means if the s is infinity, then what we have, what will be s prime? S prime will be this distance, and this point is called the focus point, right? And this distance is called the focal length. I write it here. F is called focal length. I repeat it. When the object is very far, the incoming rays come as parallel to the principal axis, right? And this is the rule. Try to understand. This is the rule in optics, that all rays that are parallel to the principal axis, they meet at same point. No matter how many rays you take, you understand my whole point? The rays that are parallel to principal axis, when they reflected from the reflecting surface, they will meet at the same point. If you have another ray like this, they also go this point. You understand my point, right? And this point is called the focus. This point F is called the focus or focal point of the mirror. So that's the rule. All rays parallel to the principal axis, right? After reflection from the mirror, they will meet at this point, and this point is called focus. That's the rule. So now this is focus, and this distance from the mirror to that focus is called focal length. And in this case, the image is formed here, obviously. When the rays are like parallel, and then object is very far, then the image formed at focus, and the image distance is called the distance from this point to the focus is called focal length, and focal length is the image distance in this situation, right? If we apply this here, for a very far object, that is s equals to infinity, right? And then the light will come parallel, and image will form at the focal point. That means s prime equals to f. Then if you plug in there, then what happens here is that you have 2 divided by r, 1 over infinity plus 1 over f. That gives us 2 over r. What is that thing? 1 over infinity. Anything divided by infinity would be anything, just that is 0. So this is 0 plus 1 over f. So this gives us the relationship between radius of curvature and the focal length. So I can just erase only this part here. So that means now we have this relationship here, that is 2 divided by r equals to 1 over f. So if it's the case, then we have the r equals to 2f. Another relationship we got, so that means radius of curvature is twice of the focal length, right? Or 2 over r is 1 over f. And if I use this equation here, everyone, in this expression, for that gives me this. Finally, another 2 over r can be replaced by 1 over f. So that will be 1 over f equals to 1 over s plus 1 over s prime. So we got this expression here, right? And this relation is called the mirror formula. So this is the relationship between focal length, object distance, and image distance, and this is called the mirror formula. They both are valid because we have this relationship here, but this is called the mirror formula. So now we have derived the mirror formula. Again, as I said before, I could have given you directly this equation, first defining all these quantities, and I could have written this directly, but I just would like to know how this comes, and this gives you a kind of uh, some kind of exercise of geometry, maybe if you have already forgotten, right? So we can just do this and we can figure out that. So this is the relationship between focal length of the focal length means this distance between vertex of the mirror and the focal point. This is the focal length. That means this is half of this. You see here, this is radius of curvature. This is double. This is half. We already got that, right? And then these are the relationship between the focal length, object distance, and image distance. Good. Okay, so we got it here. Now we already covered a number of things. So now we have these important equations here that we use this equation to do the numerical problems, and we'll be doing a few of those examples obviously because they are important, right? So how do we do those? And then these two equations, especially this one, the relationship between focal length and s prime. So we already defined that how these sign of this quantity is defined, right? And we have to take care of that also, and then we can just apply this, right? So far so good. Then I have a meeting that I need to attend around 1:20 and 25. So right now I want to stop here because we are like very ahead in the course. So I just that gives you enough time also to get prepared. So for this today's lecture, I'm stopping here. But if you want to ask me anything, then I'm recording the stopping the record here, right? Then you can ask me in the meantime. Yes. No, convex. Yes, that's not the very convex. For the convex, also the equation would be same. We don't derive that again. But only thing is that sign rule would be different for convex, obviously. No, what we learned today won't be on the exam too. Yes, Valerie, you are right. We'll be defining the S and S prime rule for the convex, right? And then we'll be using the same equation for the convex also, right? And then we'll be doing a few problem on Wednesday's class. Good. Again, I repeat, today what we learn in today's class will not be on the test. Again, test would be from chapter 21, 20, 21, and 23. Can you explain S and S prime on the concave surface? I already showed you S and S prime, right? I erased the image. S is the object distance. That means distance of object from the point B. If you go back and see the note, that's the concave one, right? So that means you put the point object there. So from O to V is your S. You are looking at the image. And then from I to V is S primed. right? So from our sine rule, that means the image is formed on the same side, since the image is formed on the same side as the outgoing rays or reflected rays, the S prime is positive, because the S prime and the reflected rays, they are on the same side of the reflecting surface, right? Okay, so now I need to stop here, right? And then again, yes, I still have office hours today. I did not do my office hours, so the office hours again will resume on Wednesday, right? There is a one message privately, so I have still office hours, and on Wednesday I'll have the office hours. Okay, good. So far so good. Okay, now again, see you on Wednesday. Stay safe, right? And now I'm ending the meeting.